So I would like to talk about what we are currently working on in my lab. So the main topic of this workshop is about releasing robots into the wild and how to basically fill the simulation to reality gap. So we are currently working on a big project funded by the European Research Council and Intel about learning to outperform humans in vision-based flight. So what do we mean by vision-based flight? So 13 years ago, I started working on vision-based autonomous navigation. And here you see actually the video that we recorded in 2009, where we believe it was the first demonstration of an autonomous drone using only an onboard camera for navigation. We were using Visual SLAM to map the environment. The environment was a priori unknown. So, and then we used this map to then localize the robot and then a standard planner in order to reach a given goal. At the time, though, we didn't have enough computing power on board the drone, so we used a 20-meter long USB cable to connect the onboard camera to a laptop there on the floor of the gym in order to do all the processing. And also, we had to secure the drone with a fishing rod because of the regulations, the legislations of the university at that time. That was 13 years ago. Where do we stand today? Today, we have already vision-based drones flying on Mars, and as you also learned this week, there will be more and more drones going to Titan, Enceladus, Venus, and also again on Mars in 2030. And they all do vision-based navigation. Where can we also find vision-based navigation? So there are companies like DJI and Schoellig that use vision-based navigation to fly drones in GPS-denied environments to both assist human pilots or completely autonomously for inspecting difficult infrastructure like bridges or power lines. But when you look at the performance of autonomous drones and you compare them to human pilot performance, there is a huge gap. And you can watch this video to understand what I mean. So if you compare autonomous drones, they still look clumsy compared to human piloted drones. So we are still very far away in terms of speed, versatility, and robustness. And why? So the question that we are trying to address in my lab is, what does it take to fly as good or even better than a human pilot? That's why we are working on outperforming human pilots. And we want to do it only using onboard vision and computation. The drone you see here is a drone that we are constantly improving, that we have been working with over the past 3 years. It's about 20 centimeters in size. It has an NVIDIA Jetson TX2 as a brain, and then we use cameras from Intel Sense as the eyes, one or more stereo cameras depending on the task. But I just want to show you a few videos of research that we have published over the past 3 years. This work was done for RSS 2020, and we showed basically how to train a neural control policy that maps images to control commands end-to-end. And this policy was trained only in simulation, and it uses onboard cameras and computation. In this other work that was published in Science Robotics a few months ago, we trained a neural control policy to teach a drone how to navigate in the wild. In the wild means in unknown environments, like forest environments, as well as, for example, training arenas, or even exiting a hangar. This drone was the Schoellig drone, by the way. This one is again our autonomous drone, flying super fast in a forest. We go up to 40 kilometers per hour. And this was all trained in a simulation. And more recently, we also started working on autonomous drone racing. The drone you see here is flying also vision-based, and it was trained in simulation. Now, why are we doing this, and how can we do this? So typically, you control robots using the classical cascade of modules that consist of perception, planning, and control. Perception usually does the estimation and mapping, then there is planning, and then there is control. And this architecture has been valid and used successfully for 40 years. All autonomous cars and other drones use it. But there are issues that we would like to overcome, otherwise we wouldn't be here at ICRA today. So the problem is that this cascading control architecture actually is very sensitive to inaccurate models of the sensors, of the actuators, of the environment, battery voltage, aerodynamic effects. It's also very sensitive to imperfect perception, which is the key problem in vision-based navigation, because as soon as you increase the agility, you experience motion blur. Also, the field of view is also limiting because the field of view is limited. So as soon as you have a very quick change of attitude, then suddenly all the features that you were using for state estimation fall outside of the field of view. Another problem is that it ignores the inherent coupling between perception and action. This is actually something that happens more for drones than for legged robots or ground robots. In order to fly, you need to constantly observe features. So, but since a quadcopter is an angular actuator system, if you want to fly to a given goal, you need to basically pitch toward the goal and then go straight. By pitching, though, you lose the visibility of the points of interest that you're using for state estimation. So somewhat you have to create a synergy between perception and control such that you always keep the features that you need to localize visible. Otherwise, the drone will crash. So this is something, for example, if you work on ground robotics, you don't experience, because if you don't see features for some time, but you won't crash. You will remain with your wheels or legs on the ground. And the other problem with this architecture is that can create latencies, because you have this cascading that basically the overall latency is basically the composition of the individual latency of all of these blocks. So on the other extreme of the classic control architecture, there will be a full end-to-end learned control policy that maps, let's say, sensory inputs to control commands. But the key issues with this architecture is that it's too sample inefficient. So how many millions or billions of images will you need so that it can generalize? So it doesn't scale. And the other problem is that such an architecture wouldn't be interpretable, which is bad, because if you want to commercialize it and sell it and certify it, how do you sell it? So what we've been working on over the past years is how can we augment the traditional robotic control architecture with learning-based methods? But the key questions are, okay, how should you train it? Supervised or unsupervised? How do you get enough data? Can you do it in simulation? And then how do you address the simulation to reality gap? So all things that we are actually focusing on in this workshop. So let me show you what we are doing. So remember the video I showed you about robotic maneuvers? That was actually trained on a non-photorealistic simulator, Gazebo. That's the environment we use to train the neural controller to learn to perform acrobatic maneuvers. This controller was trained with imitation learning, taking as input something from the sensor, I'll tell you in a moment, and outputting control commands. And then it was transferred to the real world without any fine-tuning. There was here a little bit of domain randomization in simulation, but the main trick was something else. Another thing, I showed you before the video navigating in the forest. Actually, that policy was also trained in simulation. Now a more sophisticated simulator. Here we used actually a real engine. So we imported 3D models that are made for a real engine, and then we have developed a simulator called Ingmar that basically is compatible with a real engine, Bullet, also ROS, and Gazebo. And then we basically bought from some resources online scenarios of forests. We generated them, and then we trained the neural control policy to actually perform obstacle avoidance in the wild. Also, this one was trained with imitation learning, trying to imitate an artificial expert. And in this case, it was actually a global trajectory. So since you have a simulation available, you can actually use an artificial expert. And then the neural network tries to imitate the artificial expert in the form, basically, of a global control, a global planner. But now, what is the trick to ensure that it will transfer to the real world without fine-tuning? Actually, what it made it work in the real world without fine-tuning is to use appropriate sensory abstractions. For example, for the work on acrobatic maneuvers, you can see that in Gazebo we simulated something like that with carpets and fake pictures taken from Windows desktop background. And then in the real world, you see, it actually doesn't match at all with simulation. So how did we manage to make it transfer? We use feature tracks as an intermediate sensory abstraction. And why does it work? I think it's quite obvious. Feature tracks look the same, both in non-photorealistic and photorealistic environments. So the main message is also try to think of intermediate sensory abstractions that will actually transfer better between simulation and reality. Remember when I told you about navigating in the forest? There as well. Basically, on top you see the simulated forest. It's not photorealistic, it's not Hollywood style photorealism. And then at the bottom you see what the real forest looks like. But again, we used an appropriate sensory abstraction. In this case, though it was not visual tracks, it was a depth map, and the depth map actually transfers better between simulation and reality. And it can generalize whatever the color and the illumination in the environment, because the depth maps is invariant to illumination in color and texture in the environment. However, this is just code realism. What about physics realism? We are also working on drone racing, as I told you. And in drone racing, the problem is that when you fly drones at such high speed, they experience accelerations, they go over 5Gs. And the drone flies in its own downwash. So it creates vortices. Actually, these vortices are turbulent flow, and you can only model them if you use computational fluid dynamics simulators that take hours or days to compute. So that doesn't scale. So what we are doing is that we are realifying simulators by trying to learn residual models of aerodynamic effects that cannot be explained by first principle physics models. This was a paper we presented at Datasets 2 years ago. So actually, we modeled the aerodynamic effects in our in simulation, typically using a blade element momentum theory, where basically you can basically model the full wind profile along the blades and even the bending of the blades. But this is not sufficient to explain high-order phenomena like those kind of turbulent flow. So what we do is that we go in the real world. We fly the drone in random trajectories at different speeds from 0 to 20 meters per second. We collect data. We observe the discrepancy between the desired trajectory and the flow trajectory, and then we try to model it with a neural network. So then we go back in simulation, we improve the simulator, and then you can train much better in this thing. And now what's the next step? The next step is outperform humans. And this is, for example, a human that we are taking as a baseline. This is Erwin. He's 15 years old, and he's the Swiss champion of drone racing.
Get ready on the tone in less than 5. Beep!
So you fly at 10 kilometers per hour, and you can cope with motion blur, the delay of its wave is about 1 millisecond. But what we need to take into account is that any small mistake can lead to a crash, because you are constantly pushing the quadrodos to their limits, their physical limits. So sometimes a crash it costs a lot of money and a lot of time to my researchers. This is another. So anyway, we are working on that. And what I want to conclude by saying that basically the main message we want to give is, there are also the strategy to reduce the sync-to-real gap. So we are aware of domain randomization, real-world adaptation, but there is also the trick of finding the appropriate sensory abstractions. So think about the sensory abstractions for your task. Also, what we found out is that it's not just the sensory input abstraction, but also the output abstraction plays a role. So we have a paper at here where we actually showed that if you want to do agile maneuvers, it is better actually to not regress individual rotor thrusts, but rather collective thrust and body rate. It transfers much better to the real world. Okay, thank you.